Rational functions and their graphs. This is an example of a rational function. It is a ratio of two polynomials. It's a fraction. And like any fraction, we're concerned about the domain. We've worked on this recently, and in a fraction form, you have to check the denominator. Denominators cannot be zero. And so that's what we're going to look at. How do we find its domain? The domain starts with the set of all real numbers, and then it has to throw away anything that makes the denominator zero. So all we care about is the denominator. If we're looking at domain, we set it equal to 0 and we solve. This one we can factor out a GCF. So x squared times x minus 2 equals 0. And then set each piece equal to 0. So x squared equals 0 and x minus 2 equals 0. This one's already get solved. If you take the square root, it's plus or minus square root of 0, which is still 0. This one, add your 2. Right, remember these are values that you're going to throw away. And this one asks us for set builder notation. So it is the set of all x such that x is an element of the reals and x is not equal to 0 and 2. We'll find the domain of the following rational functions. So for the first one, we will just go to the denominator, set it equal to 0, and solve. This is a difference of squares, or you could move the 121 over and then do square root method. I'll just do difference of squares. X plus 11, x minus 11 equals 0. And this will be x equals negative 11 and x equals positive 11. Remember, you're going to throw those out. If you're using set builder notation, the set of all x such that, and I'm just going to write the rule piece, x is not equal to negative 11 and 11. I think that your software sometimes asks for interval notation. So let's also do interval notation. So it's going to be the set of all real numbers except these. So you're going to start left to right. So you're coming from negative infinity. You're going up to negative 11. You have to use parentheses because you're throwing that out. Then you start again at negative 11. You go to positive 11, parentheses on both ends because you don't want either negative 11 or positive 11. And then you'll start up again at 11 to infinity. Right, the other one, we set this denominator equal to 0. This one is not going to factor. You can move the 5 over and use the square root method. But you see that you're going to get a complex number. So you're not going to have anything to throw away on this one because you're starting with a set of real numbers. So this one is going to be all reals. So it will be negative infinity to infinity. An asymptote. An asymptote is a line that the graph approaches but never actually touches, as either the x or y values get extremely large. We denote them with dotted lines on the graph. When we have a rational function where p of x and q of x have no common factors, and A is a 0 of q of x, and that means when you set q of x equal to 0 and solve, that's what you get. Then x equals A is a vertical asymptote. So you actually do the same work that you do to find domain, except you're not going to throw it away. You're going to make a vertical line there, and your graph will actually blow up at that point. So to find a vertical asymptote, set the denominator equal to 0 and solve. They are vertical lines, so this will be the equation x equals. Right. What is the relationship between domain and vertical asymptote? Well, you do the same steps to solve. For domain, you're going to say, okay, x minus 3 equals 0. You solve, but you're throwing that away. And then you either write it in interval notation or set builder notation, but this is what you're doing. You do not want x equals 3. When you're doing vertical asymptote, you set it equal to, we'll call this VA, vertical asymptote. You take that denominator, you set it equal to 0 and solve, x equals 3. This is your vertical asymptote. It's a dotted line on the graph, and the graph will move away from it. So this is 5, so I'll try to draw this. So it's going through x equals 3. And as you get very large or very tiny values, they go toward that asymptote. Find the vertical asymptotes, if any, and the values of x corresponding to holes, if any, of the graph of the rational function. So this one doesn't have any holes, and we'll look at that on the next problem. So we'll say no holes with this one. But to find the vertical asymptotes, you just take the denominator, set it equal to 0, solve. So x equals 6 is your vertical asymptote. So that would be your dotted line on your graph that the graphs will go toward. Right, so we would pick our answer. The vertical asymptotes is or are, so there can be more than one. And this one says no holes. We have no holes. So this one is going to be, I'm just going to have to write it above, x equals 6. Right, and this would be the choice. Here's another example. We are going to find the domain, and then we're going to find the vertical asymptotes. So it has to do with the denominator. The denominator can't be 0 when you're talking about domain. So we're going to set x squared minus 4 equal to 0 and solve. And so this is a difference of squares, or you can move the 4 over and use the square root method. So it is x plus 2, x minus 2 equals 0. So we're throwing values away with domain. We have the set of real numbers, but we're going to throw away negative 2 and positive 2 when we set those equal to 0. So x cannot be negative 2 and positive 2. And use whichever notation that they tell you for that. So make sure you say cannot equal when they're asking you domain. For the vertical asymptotes, it's the same work. We set the denominator equal to 0 and solve. We'll factor. That is a 0. So this one, you subtract your 2, so x equals negative 2. That's the equation for a vertical line. This one, add your 2, x equals positive 2. That's the equation for a vertical line. So this one has 2 vertical asymptotes at 2. Right, and I can't make this thin enough, but I'll just do it a little bit. Your graph is going toward it. This piece of the graph is going toward it. And this one, as you go down, is going toward it. It's not going to touch it, but it goes toward it. -2 is here. And your graph is going toward it. Up here and down here, but it's not going to cross it. So what are holes? Holes occur when your numerator and your denominator have a common factor. So if we factored this out, our denominator and numerator have a common factor. This is x plus 2, x minus 2, and this is x plus 2. So the piece that would cancel out is going to leave us a hole at this denominator at the value. So at x equals -2, we will have a hole. This piece set it equal to 0, but it's canceling, so it's not going to give us an asymptote. So x equals -2 gives a hole. The other piece will still give an asymptote. This simplifies and gives us 1 over x minus 2. But this one is going to give us a vertical asymptote at x equals 2. And I'm going to pull this up on the graphing calculator. Right, so we did one just a minute ago with x, just x on the numerator over x squared minus 4. And remember, it had 2 vertical asymptotes at +2 and -2. But this one, because the piece canceled off, you will get a hole at the x equals -2 instead of an asymptote. So at x equals +2 is your only asymptote. That is like a dotted line. It's not really a part of your graph. Next, we'll look at horizontal asymptotes. To find a horizontal asymptote, we're going to use this little chart, and it's going to be based on the degree of the numerator and denominator. Horizontal asymptotes are of the form y equals something, and horizontal asymptotes may be crossed. Right, so it all depends here, you'll see, on whether the numerator degree is less than, equal to, or greater than the denominator degree. And over here is what you do, depending on your situation. So when we look at these, we're looking for the horizontal asymptote, we're looking at degree. So the degree of your numerator on this first one is 1. Of the denominator, it's 2. So your degree of the numerator is smaller or less than the degree of the denominator. It is your first situation, so your horizontal asymptote is y equals 0. For the next one, your degree of the numerator is 2. Your degree of the denominator is 2. So these are equal. So your line will be the fraction of the leading coefficient of the numerator over the leading coefficient of the denominator. So y equals 12 over 6, and you should reduce that. So y equals 2 will be the horizontal asymptote for this one. For our last case here, the degree of the numerator is 3, the degree of the denominator is 2. So it is our third situation. The degree of the numerator is larger than the degree of the denominator. So this is going to be none, or in your software, it will be does not exist. Next, we have a strategy for graphing these rational functions. These are ones with no common factors. So first of all, we will find the vertical asymptotes. Set the denominator equal to 0 and solve. And putting those on the graphs will be our dotted lines vertically. Find any horizontal asymptotes choosing our degree rules. Then we'll find the y-intercept, which we have done many times, and this is when you set x equal to 0. So plug in 0 into any x's. And the x-intercept, if there is any, by solving p of x equal to 0, right? And so normally, so let's talk about number 4 here for just a minute. Normally you set y equal to 0, so you set the whole function equal to 0. To solve for an x-intercept. But when you have a fraction, if you get 0 in the numerator, 0 divided by anything is 0. So if you have 0 over 7, it's 0. If you have 0 over 243, it's 0. So you don't care about the denominator in this situation, just the numerator. So that makes it a lot easier because it's going to be 0. If this numerator is 0, then that's all you have to worry about. So set p of x equal to 0 and solve. All right, so that's for x-intercept. Plot one point between and beyond each x-intercept and the vertical asymptote, and use the information above to graph the function between and beyond the vertical asymptotes. Also, don't forget you can have your graphing calculator. So we're going to also pull up our graphing calculator, but I want you to be able to do these by hand. We're going to go through the steps and do an example. So we're going to graph the rational function 2x over x plus 2. First, we want to find the vertical asymptotes. So we take the denominator, set it equal to 0, and solve. So x equals -2 is a vertical asymptote. For the horizontal asymptotes, remember you use your little table with degrees. Your degree of the numerator is 1. Degree of the denominator is 1. So y is going to be equal to the fraction of the leading coefficients, 2 over 1, which equals 2. So y equals 2 is your horizontal asymptote. Y-intercept, you plug 0 into x, so you have 2 times 0 over 0 plus 2 is 0 over 2, which is 0. So 0, 0 is the y-intercept. X-intercept, you plug, for this one, remember, you only have to do the numerator equal to 0, not set the whole y equal to 0. So set your p of x equal to 0. So just your numerator. And divide by 2. So this says x equals 0. So this one is also 0, 0. And next we'll get some points in between and beyond, and they suggested those to us. I'm going to go ahead and put the first 4 things on the grid. So first of all, our vertical asymptote, x equals -2. So we'll try to do a dotted line. X equals -2. A horizontal asymptote at y equals 2. So it kind of breaks your grid into 4 sections. The x and y intercept, which is 0, 0. Right, and so if you had to choose your chart, you would choose something over here in this section. So that's why they have a -4. Not sure why they have a -4 and a -3. Right, but a -4, -1 is good. It's between your vertical asymptote and your intercept, and then something over here. All right, so let's go back to our chart now, and I'm going to just erase real quick. All right, so -4. So you have to plug it into all the x's. So 2 times -4 over -4 plus 2. This is -8 over -2 is a +4. Then -3, 2 times -3 over -3 plus 2 is -6 over -1, which gives us 6. Right, -1. 2 times -1 for -1 plus 2 is -2 over 1, which is -2. Right, and then we'll do 1. So 2 times 1 over 1 plus 2 is 2/3. And 2. 2 times 2 over 2 plus 2 is 4 over 4, which is 1. All right, so now let's get these points on. So -4 and 4. So, sorry, -4, 4. I can't press down hard on that. Right, -3, 6. So you can tell your graph is going toward this asymptote. -1. So you can even fill this on. It's going to go like this. Right. -1, -2. 1 2/3. So about right there. And 2 and 1. So this piece is going toward that asymptote and toward this asymptote. So there is your graph. Let's pull up the graphing calculator. And we'll turn it on. And I've already did y equals. I did want to show you this to remind you when you put this fraction in, you need parentheses on your numerator, parentheses on your denominator. So parentheses, we have 2x, close your parentheses, divided by parentheses, x plus 2. Close parentheses. We'll say graph. All right, and your calculator does not put on the horizontal asymptote. Right, so these curves are the part that is your graph. This is the vertical asymptote, but you can kind of see where the 2 falls here. Those go toward it. And the other thing we can do here, if we are doing a problem where we have to show the points, we could actually use table. So do second table, it's above graph. And, right, so there's our -4, 4, -3, 6, -1, -2. You can't pick -2, that's why you get an error, because it's not in the domain. Right, it would give a 0 in the denominator. Right, 1 2/3, that fraction would round off there. And 2, 1. All right, and so there's our graph. I had mentioned when we defined the horizontal asymptote that the graph could cross the horizontal asymptote. So let's see what we have to check to tell if it crosses the horizontal asymptote. So we found the horizontal asymptote is y equals 2. So we'll set our function equal to 2 and try to solve. So we'll set 2x over x plus 2 equal to 2. And we'll just do this as a proportion. So make this 2 over 1, and you do your cross products. So we do 2 times x plus 2 equals 2x times 1, which is 2x. So this gives us 2x plus 4 equals to 2x. And you have to subtract x from both sides. And so the x is going to cancel. And you get 4 equals 0. So it does not cross. You do not get a solution here. So it does not cross. But that is what you would do to find out if it crosses. And it's still going to be very close to it. Let's look at another example. So here is our function. And first we'll find the vertical asymptotes. So we're going to set the denominator equal to 0 and solve. So x squared minus 16 equals 0. So this will be x plus 4, x minus 4, difference is squares, equals 0. And so x equals negative 4, x equals positive 4. Those are your vertical asymptotes. A horizontal asymptote, you work with your little table and your degrees. Your degree of the numerator is 2, degree of the denominator is 2. So this will be y equals the fraction of the leading coefficients, which is 1 over 1. So it will be y equals 1. Right. Y-intercept says plug 0 into x. So you're going to have 0 squared minus 0 minus 2 over 0 squared minus 16. All this is going away. So you have negative 2 over negative 16. Your signs clean up to positive, and this will reduce to 1/8. So 0, 1/8 is a y-intercept. X-intercepts, remember you're just going to set this numerator equal to 0 instead of the whole function. So x squared minus x minus 2 equals 0. And you can factor. And we can use 2 and 1. So 2 and 1. And this will be x equals negative 1 and x equals 2. So negative 1, 0 and 2, 0. Those are x-intercepts. So let's put this info on our graph. Vertical asymptotes, we have 2. We have negative 4. X equals negative 4. And we have positive 4. Our horizontal asymptote, y equals 1. So you have more sections on this one. All right, a y-intercept. So don't go over, but go up an 8, so just a little tiny bit. And x-intercepts, negative 1, 0. And 2, 0. Right, and here was your y-intercept. So you can kind of tell this one is going to go this way without even those other points. Right, and now we'll get our other points. I think I'm going to just pull the calculator to get these. So I'm going to go ahead and put this in our calculator. but you saw how to do them by hand before. All right, we'll get it on. We'll clear. Y equals clear. And we're going to type this one in. Remember, parentheses on your numerator and your denominator. So x to the second minus x minus 2, close your parentheses, divided by parentheses x squared minus 16, close parentheses, graph. All right, so we had this one piece right, and we didn't even get the points yet. We're going to go into second table, or we could do second count value and get those also. Second table, all right, and where it says error, that is going to be your vertical asymptote, because that's not in the domain. So we wanted a -5. Oh, so this is, we would have got a fraction there. So let's see how I can make that stay on if I get it over there. 3.1. Okay, it's not going to stay on. All right, -2 is -1/3. 0 is 0.125. That is your 1/8, which we already have on there. 3. -0.57. Boy, I'm glad I didn't try to do these by hand. And 6. .4. All right, let's just kind of check on those. So we needed something out here, and so -5 says 3.1. So about right here. So this tells you this section is going to go toward this asymptote and toward this asymptote. All right, -2 is a -1/3. We already had that part figured out, so -2 and -1/3. So I should have really been up a little tiny bit here for a better graph, but it's pretty close. All right, 0, 1/8 we already had on there as the intercept. 3, so about -0.6, so a little bit more than -0.5. So 3. So about right here. And 6, so something out in this section past this vertical asymptote. So 6 and 1.4. So it's up here. So this section is going to go toward this piece and toward this. Now let's look back at our graph and see if that is how it looks. We'll hit graph, and there we go. Very good. Let's look at one more question. Does it cross the horizontal asymptote? Remember, it can't cross a vertical asymptote because that would put a 0 in the denominator. But it could cross a horizontal asymptote. And so let's set the function equal to the horizontal asymptote. So x squared minus x minus 2 over x squared minus 16. Does this ever equal 1? And again, you can solve it like proportions. So do your cross products. So x squared minus x minus 2 equals x squared minus 16. So subtract your x squared from both sides. So negative x minus 2 equals negative 16. And you are going to add this 2. So you get negative x equals negative 14. And divide by negative 1. So you get x equals 14. So we get a solution. This one actually will cross the horizontal asymptote at the point 14, 1. It will cross, which is way out here. Let's see, I don't know if we can pull it up on their calculator. We'd have to change our window. So we would need to see 20 on the max. Right. See how it's still going to go very close to it, but it actually will cross it there. Let's look at one more example. And so first we'll find the vertical asymptotes. You're looking at your denominator, setting it equal to 0. And so this is also going to be a difference of squares. So x plus 1, x minus 1. So x equals negative 1 and x equals positive 1 will be our vertical asymptotes. Horizontal asymptote, you will do with the little degree table. Your degree of the numerator is 2. The degree of the denominator is also 2. So they are the same. It will be y equals the fraction of the leading coefficients, 1 over 1, which is 1. So y equals 1 will be the horizontal asymptote. A y-intercept, plug 0 into x. So you have 0 squared minus 2 times 0. So you get a negative 15 over, this is 0, a negative 1, which gives us positive 15. So 0, 15. That's going to go off our table. It's important to remember that, though. All right, and x-intercepts will be set the numerator, the p of x equal to 0. So x squared minus 2x minus 15 equals 0, and we can factor and solve. So different signs, and looks to me like 5 and 3. So if we do a minus 5 and a plus 3, and so this looks like x equals negative 3 and x equals 5. So we have a negative 3, 0, and a 5, 0. So let's put these on our grid. So first our vertical asymptotes at negative 1, x equals negative 1, and x equals positive 1. All right, and then our horizontal asymptote y equals 1. Y-intercept is 0, 15, so don't go over. It's way up here. So when we look on the graphing calculator, we need to change and not forget about that section way up there. That is out of our window on this grid. And so negative 3, 0, negative 3, 0, and 5, 0. Right, and this kind of tells us, without more, some of it. Down here, it's going to look like this. And this one, it's going toward this asymptote and this asymptote. And you need to know what it's doing in here, right? So this point is way up here. So we'll go to the calculator to get these values. And I already typed it in. just to save us some time, remember your parentheses, and I graphed. So it doesn't show your horizontal asymptote. But we still need to look at this middle section. Remember I said way up here? So we need and that was 15. So let's change the window on here, and then we'll get our points. All right, so if we change our window, and we need to go, that would be the Y. The X's are fine. And it's actually the Y max that we want to see higher. So let's see it go to 25. Right? So you can see in there you're getting a little loop up. So at this piece on our grid, it's going to turn up toward those asymptotes, not back down. Right? And it will continue that way. So you don't want to forget that piece of your grid. Let's see if I can even make, let's do our X-Men. Let's look at that one section a little bit more. And let's make X-Men a -5 and X max a 5. Just so we can see that center a little bit better. There we go. Yeah, we can see it. All right, so we wanted to get our values off of here because Mrs. H is being lazy. All right, so -4. All right, it's 0.66, which is, we'll just put 0.6. All right, and for -2, it's -2 1/3. For 0, it's going to be 15. That is your y-intercept. For 4, and I could have just typed in a 4. So -4.6, so about -0.5. Sorry, 0.46. All right, and 6. So if I didn't want to keep using that scroll, I guess it's not going to let me do it. I thought it would just let me enter it. All right, so 0.257. So was that negative or positive? So that is positive, 0.25. So a little bit more than 1/4. All right, so -4, and we got 0.6. And that is about where I've drawn through. It's a little bit more than 1/2. So just to verify, -2 is -2 2/3. So that's about right here. 0.15, we've got that one on there. 4 is -0.4, so about a -1/2. And we did pretty good drawing that. And at 6, your 6 is here, it's 0.25. So I took that up a little too high. And you could kind of tell that on your, it's a little bit more down like that. But that's a good job there. We'll check if it crosses the horizontal asymptote. So you take your whole function and you set it equal to that horizontal asymptote. So x² minus 2x minus 15, x² minus 1 at 1. So again, we'll do it like a proportion, cross products, and it's actually when the numerator equals the denominator, that's when you get 1. So subtract your x² from both sides, they will cancel. This one is going to give you a solution. So add your 15 to both sides. Gives us 14. And divide by -2. So at x equals negative 7, this will cross. So the point will be negative 7, 1. This will cross the horizontal asymptote. And we can pull it back on our calculator. Graph, let's put our window back to standard. All right, and I said negative 7. So at negative 7, 1, 2, 3, 5, 6, 7. So about right here it crosses, but it still stays very close. We could also see that in our table. All right, when the y is 1, right there, negative 7, 1.